great to be here and great to see so many familiar faces. I have had a number of Teams meetings and email exchanges, and all of a sudden lots of familiar faces here. So today it's about Artwave Surf and the application of our technology in the river surf conditions. Based on my discussions around, it's like 3 years, different places in Central Europe, Germany, Austria, Switzerland, even in the US we have had these discussions how to implement this technology in rivers, and now I will give you the insight. But before that, a couple of words about our approach. So we started like 10 years ago, and our design principle is like doing as little harm to the nature as possible. Everything is mobile, we can live with no trace, and we believe that the water wants to make waves, and actually that holds. It's amazing. And to put it in a nutshell, you put some energy into the water, being that flowing river or then it's wind, something that puts the energy into the water, and the water forms waves afterwards. And that's the trick we actually, or one application of that trick, what we found. This picture here, you can say it's from our test site. It's actually up and running. You can come there, and as a kind of courtesy gift or kind of how I can support your activities, you will have 1 free hour of surf if you travel to Finland. Yeah, you're welcome on the site. And there you can see our test surfer, and then that stick is now taken away. It is our measurement. But yeah, it's in the middle of forest, and some of you have been there, so we have evidence. This is in a nutshell what happens. The container is on the shore, and there we have the engine, and then we have wire rope system and the pulleys, and then a fixing point here, which is not mandatory, but it facilitates the reverse of the wings to the starting position. And the wings move towards the container in the depth of 1.5 meters. And as you can see, the surfable wave takes shape on top of the back wing. And kind of thinking of rivers here, so the wings move from here to here across the water, and the wave moves on top, kind of on the surface, and that creates a kind of surfing experience, which is quite. People say that it's and I can say that it's like natural surf. The wave is not exactly like an ocean wave. There is a little drop in front of it, but when you surf, it is like I'm on a wave and I'm surfing. Yeah, it's great, and we are still amazed. After years, we are still amazed that we are able to do it, and that's kind of the simplest possible application. And now you are in the river surf world. We make the wings move in the basic setup. How about if we fix the wings here and we make the water move? There you have the river. And that is kind of in a nutshell, the idea here. We apply all the same principles, findings we have found here, which we have examined, and we can apply them in river conditions. And now my presentation is about kind of what you could do to create that kind of conditions. And this is kind of the basis for all my dialogue with different river surf representatives. Yeah, it's pretty simple, and kind of what I want to say still is that when you have the river's waves which you surf, there is kind of the slope down, and then it goes up. It is basically the same shape you have already, but it's fixed And now we are kind of the novelty here is that this is a floating wing structure that is mobile. So you put it in the river and you can take it out from the river. Shortly, briefly about our company. It's 10 years old. It's based on Aalto University 2-year research project where we have had like a multidisciplinary project. We had like 5 students doing their thesis work, and then we had the professors involved, and we were planning and testing and kind of finding the approach. And what we found was a that our invention was patentable. That was the first thing, and then we got funding from the university, and we were able to expand it. So it had 2 streams. We had the prototype construction project, and then we had the patenting project. And my role there was to do the coordination and be involved in both sides, so the patenting, but also the technical details we were discussing there. 2014, we were able to do the pilot testing in Kalasatama dock pool, and it was a successful case. We were able to be there, kind of validate our approach, get the results for the project, and then we kind of created the startup, and of course all the challenges and problems followed. We had the patenting stream globally taken. On the other hand, you can see that there is no mention about the kind of continuation of the test site. And that was so difficult. And comparing to your challenges, it is something similar. We tried to negotiate with cities in southern Finland how to do it. And they all said that, yeah, this and that, and kind of we can rent out the space for you against a large sum of money. What happened was that we ended up buying our own land and created the test site there. And that is actually really interesting. So we are able to do it there, and it's globally the only place where you can actually kind of freely operate it. Our application of the man-made waves. However, there are other things into the when you do waves associated with it. The aeration is one thing. You have like kind of troublesome bodies of water. Also here in Central Europe, you have algae, too little oxygen in the water. When you make waves, there is the white water and the curls, and that oxygenates the water, and that is actually good for the body of the water, and that is a surprisingly positive impact on biodiversity and the nature, and that is something we have kind of considered. And let's see what happens if we have news at some point on that front. And then you can see the RC, and this is in our core. It's remote control. So here you can see the wires. We want to get rid of those wires, and now you have followed the. I hope you are following the Ukrainian war and the sea drones, and the technology there is that they are self-guiding. We could apply the same technology here, self-guiding waves, and that is where our core is, and that is why it would be great to have cooperation with you guys, so you know the rivers and the conditions there, and that is where our kind of core competencies are. We come up with the crazy ideas that you can combine these technologies like cross-disciplinary way, create something you have never seen before. And yeah, test site development, production testing 2022, 23, we had like this, 22 we had the insiders there, 23, 24 we had like it semi-open, and this year 25 we had it like full-blown open, and it has been so crazy summer. I'm like in burnout. Like we intended to have it 2 days per week open, couple of hours. We ended up having it open 3 to 4 days per week in July and August. And then we had to do the maintenance, so it turned out to be a full-time job. On top of my other day job, I was working on the site, doing the maintenance, getting it to kind of the clients, and the demand has been a very positive surprise. Even tomorrow, we will have a surf workshop, and 16 surfers will come to the site, and the water temperature is now below 10 degrees Celsius. So they will be there the whole afternoon, and we will be giving them a surf workshop. So it's a demo use for us. So it's a demo site. It's not the production facility. It's a demo site where we develop the technology all the time. And what we are doing there is to kind of observe how the parts wear out and how they are stressed, and kind of great to have the time over the winter to look into the kind of core of the system, what is wearing out, and how the system is doing after a very intensive season. Another thing which I have already discussed today is that in river surf you have the wave there, and this location here is like additional part of it. What we have in Artwave Surf is kind of the concept for all the other activities around it, and this creates kind of a viable system and critical masses here, as you have the skate park here, and then you have the wave, and then you have even the canoeing there. That's a good idea to have a kind of location for activity sports. But yeah, here another slides on the nutshell, and this is the core message. If you have any questions or doubts, feel free to ask the questions. So basically, it's the diagram over there. When you increase the speed, the velocity of water, you are able to increase the size of the wave. And this is what really happens in rivers as well. If you are able to do like 2.5, 3 meters per second velocity, then you will have a decent surfable wave. If the speed of water is lower, you can do a whitewater wave for beginner purposes. And now the safety thing is very good here. If you want to expand the sport, it is now meant for experienced surfers. But if you want to expand it, you should be able to do kind of a intermediate beginner waves with white water and have the lessons there, make it safe for everyone to surf. And that is what, let's say, societies at large need: more like physical exercise, more motivation to do the training. But that is the diagram, which is very important here. And you can increase the wave height with speed. And how to generate speed is then the question. How to put energy into the water so that the waves are possible. And here, if we think about shortboard waves, you need 4 meters per second of velocity. And what I have found out and came across in all our discussions, the speed of the velocity of kind of average river in Central Europe is there 0.9, 1.1 meters per second. And that is the challenge which we have to overcome somehow. Kind of need to increase the speed, and what you can do there is to kind of, and what you are actually doing here also, you can see that you're squeezing the water into a small passage, and then you create the wave there, and there you have the slope and the ramp, and that's where the wave is. And yeah, that's basically the starting point, and it's a pretty straightforward equation. And approach is to resolve that, a sustainable setup. And that is from our CFD model, a picture there. No permanent changes in structures in the riverbed, wings assembled to riverbed. Kind of we have one experience in Finland we have ice there. Of course, we have ice, and in winters the ice is also in the river. So bridge pillars are quite sturdy. They are like heavy-duty pillars, and we had this project and said that maybe we could kind of attach our wings to the bridge pillars, and how about the forces there? And the guys who kind of look after the bridges said that what are the forces you need, and our kind of requirement was like really a fraction of their kind of thinking, their perspective, and it was easy to kind of assemble that into a bridge pillar. And this is something immediately in Central Europe, the person responsible for bridges says that the pillar is like sacred, and the forces we need to use there are quite small after all. So kind of if it endures fluids, it should be able to take carry the wings. But yeah, that is the dialogue you need, and so that is one way to actually attach the wings or have the fixing points in the bridge pillar. Other approaches are like having concrete blocks in the river or some fixing points on the riverbank. And here we had the CFD model where the parameters was 1.1 meters per second, depth 2.5 meters, wing chord 5 meters, so it's quite wide. And this is the trick which is comparable to aerodynamics. If you have a fighter, small wings, high speed, it's in the air. If you have a kind of slow speed, you increase the wing size, all the dimensions, and it keeps in the air still. The same principle applies here. So if you have a slow river, you create massive wings, and then you speed up the kind of water flow with the wings. And if you have two wings, then you have the interaction between the wings, and you are able to create the wave. But it's the question of energy in the water. If it's really still water, you have to use engine to pull the wings, and then you have a combination. Massive waves, easier to create. Setup for two-wing system is the thing there. In the right-hand side, lower corner, you can see a picture of our kind of CFD model, which we used for Artwave system. And there you can see the trick that this is one of the secrets. There could be more wings, not just one or two, maybe three, even more. And here you can see this is what we have patented. First it goes up a bit, accelerates even more, and amplifies, and that's where the wave takes shape. That's pretty. It's awesome. It's pretty simple after all. Ways to increase flow. Use vertical drop. That is kind of the easiest thing, and that is what happens, or that is the solution for majority of cases. You have here also you have the drop, and that's used for it. Otherwise, decrease river cross-sectional area. So that means that you kind of squeeze the water into a smaller passage. So, and then it accelerates. That's like in the pipelines, and the pressure increases. Other easier way is to squeeze the banks. And well, how to do that is something that you can do like permanently. That's fixed construction, and that's the traditional approach to this. But we have done cooperation with maritime industry, shipbuilding industry in Finland, and they do this Royal Caribbean Cruise Line ships for the oceans of the world. And our systems are so small compared to what they do. When they consider forces, those are like 10 or 100-fold, 100 times larger than the forces we are using. So creating, squeezing kind of construction based on steel let's say, wings or flaps on the riverbed that are hydraulic is totally doable for maritime industry. If you think about oil rigs, ocean ships, that's kind of basic stuff there. They can do it like overnight, but that's totally new and an urban setup. And that is the trick here. You can consider it, you can do it permanently fixed, but you can do a construction that you can lift up and take it away if the fluid is coming. And it's based on steel or even some other materials like fiberglass. And that fiberglass is quite, or then carbon fiber is even cooler material, but that's really expensive. You can use that kind of solutions there. And the flow thing is there that you can optimize the flow, and that's a kind of combination of the how much more water you have, what's the velocity, and what is the material of the squeezing device. That's another approach. And this is what we more details about. This is based on one of my discussions where we went to the level how it could be implemented, and this is something you can do actually with CFD analysis. You just analyze you get the dimensions from the river, the material in the river, and then you start modeling it. And that is maybe the message of this slide, is that it's a good idea to do simulation model. Maybe today you can do it even on a laptop. The computational power has increased a lot compared to what we did in our first simulations 10 years ago. So it's pretty easy to do and to find if it's feasible or not, and then develop the thinking there. And then the next question is water level. When you start squeezing it, then you think that the water level increases immediately. But that is not the case necessarily. If you have a smooth surface there, so the friction decreases, and then the velocity is higher, and it's smoother at the sides, so the water level doesn't necessarily rise as much as you could imagine. And this is also something you can model actually with the CFD modeling. And this is not going today into the details. This is the equation, and here you can have the reverse physical properties, and that is where it's case by case. It's case dependent what you have there and how to do it. But it's this is basic physics after all. And then another approach, concrete block approach, which is basically you create a dam, like underwater dam there, and then you can this is related to one other case we were discussing, that the riverbed had like a drop there, and then we could do some kind of modification there so that the riverbed is dropped there, so that we can increase it here, and then create the upper surface of the wings. So you have one concrete block, and you have the wings there, and that creates the phenomenon I showed you in the other picture, what we have in the CFD model. And so where you have the ramp, and then you have the flap there, maybe you could apply wing profiles there to optimize the formation of the wave. And that is also something you can really easily model in simulation models. And the concrete block could be designed so that it's heavy enough so that it keeps in place on the river floor, but it could be like elements there, so that you can lift them off in off-season. Or if the fluid is coming, you lift all the elements off, and you modify the riverbed for temporary use of it. This is a picture of from one of my trips to Portugal. It's a bit unclear. I kind of with this I want to illustrate the another kind of property of the water. Maybe you have seen this. At least you can see the kind of the in Hawaii they have this when they open up the kind of freshwater pocket, and then the water flows to the ocean. And there you can see that the surfable wave takes shape on top of like a bumpy road. So they have bumps there. And this is very small, but you can see the bumps there. And when I was filming this, it got rogue. It is so strange. It was kind of fluent for a while, and then something happened, and it started to get rogue there, and then it like jumped here. So it was amplified. And I've seen it in real life, and then we were able to kind of establish the validation in the CFD model. So it can be, and this is another approach, wing slope. Based on concrete block, yeah, this is for kind of a combination of the previous slide, and then you do a fake riverbed that is kind of a bumpy road, and it requires a mechanical kind of land engineering, and this is kind of the end result. I'm really bad at drawing anything. I just have the kind of abstract ideas. But here you can see that there's the drop. So the river level here, and this bridge is just a kind of establishing a restriction what you have to kind of overcome. So it can't be higher than that. It needs to go down. And if you apply number of these wings, as I said, we were applying 3. If you apply 4, and you get it like amplifying first a little and then a little more, and then you get the real amplification here. That is one new approach to consider how it could be done. And it is simply kind of something you can assess in CFD model. What happens, and the kind of a good challenge and a question for anyone if you are in the university, if you are considering CFD modeling there, if you have anyone who is studying there, someone close to you, this is a very good suggestion to do kind of that kind of modeling. But this is something we are exploring currently, that if we do a wing slope application, and it is not permanent. You can have the slope there, and then all the components can be like separate, so that you attach them together so that you can remove it easily. But yeah, then a couple of final words about the planning work. I've said many times the CFD modeling, the feasibility study, and you might be familiar with this, and this is what we kind of think about this. First you need to do the feasibility studies and validation, and this is connected to your local discussions with the permitting authorities, how they think about this. Then you create a technical concept, you design it, then you have to evaluate it, and then production and maintenance follows. But when we are here, we are mostly on the kind of in the first 2-3 phases of this. So the technical analysis, simulations, and what we can deliver, how we can support you as the feasibility report, parts of it, and specification document, or then the actual prototypes. So when we are talking about these technologies, we could do a small prototype at first. In Austria, we had one case where we tried to kind of jump into middle-sized prototype immediately, and it failed. In Joensuu, Finland, we tried to do kind of the final product immediately. It failed because you have to kind of step by step understand what you're doing, and that is kind of one of the lessons learned on my journey in this river wave design world. But yeah, possible prototypes and then small scale testing. That would be a good idea. Yeah, I have no further ideas. Thank you. If you have any questions now, it's a good opportunity to ask them or have a discussion, or maybe afterwards.
So actually, Matt?
Yeah.
So actually, you have responded my question I had in my head during your presentation. One last question is, at one image you showed that they were at the end of the wing, there was creating vorticial vector, very vorticial flow. That means that it might, like we are talking about safety. With these constructions, have you studied also what is happening behind the last construction?
Yeah.
Vorticial vector field that might not pose a risk.
Yeah. Yes. A very good, very good question. So what happens around this? Yeah, and here you can see turbulent flow, and the difference between laminar and turbulent flow is crucial here, since that is the breaking point, is where the change happens. And for surfers, that is something which should be here. But what happens after the wave is as important, since there, if the turbulent waters continue, that is bad for there could be erosion problems and challenges, and that is actually what we did. We established one part of our analysis is that we established the boundaries, so that the kind of when we pull it's better in this picture. We created actually this so that when we pull in the wings here, we created analysis what happens here, but also what happens here and what happens here. So we have a full understanding of the surrounding area, and this is really important for the erosion and environmental impact. But yeah, and it's really interesting, and this is actually the reason why we have the minimum requirements here. So we have even measured the size of particles that move here, and that is doable in CFD analysis. That what is the size of the particle, the mud here, or the sand, or the gravel? What kind of materials you should have at the river, or when you have lakes, you can have mud there. River beds are easier since they are quite fixed because of the flow. Yeah.
One very practical question, so referring to your prototype, which we can see here. How deep under the water are your wings?
Yeah, here this is 1.5 meters.
Okay.
Yeah.
So just a practical question. So how many waves can you per hour? And how does the water look like after your wave? So do you need some time to wait that the water gets smooth again?
Yeah, so it depends. Of course, what I can say from our real life experience is that we produce 30 waves per hour. And we can do that kind of continuously. So we stop the wings here for, let's say, 5-10 seconds, then we reverse them slowly, and then we stop them here like for 5 seconds, and then we pull the kind of power pull in, as we call it, takes like that 20 seconds or something like that, and that is like 30 waves per hour. So during the reverse time, the lake settles down. But we have evidence that it creates a certain current there, that the more water capacity you have around, the easier and it is to operate, and the better is the profile of the wave. But those are modifiable, so that you can increase the speed, you can increase the river speed as well. You can do two-directional application of this. and then you get like the wave frequency like more than doubles that. But that actually, based on our experience, we have like optimally 4-5 surfers in the water per session, and they actually like it, that it's one directional. It's like natural wave, and then they paddle back to the lineup, and then they have the circulation what they have in the ocean.
I have one question. How high is the energy consumption, and how is efficiency compared to other systems?
Yeah, good question. And it was 3 kilowatts per wave is one, but that's totally comparable to other waves and the wave technologies. And we have old generator set there, and we are burning like 25-30 liters of gasoline per hour. And that is a very good kind of, that's real life kind of energy consumption there. And the cost of running the system is kind of the higher cost is to have the personnel there, the people there, but the fuel cost is reasonable.
Okay, thank you.
Yep.
It's an easy question. How did you decide on the name Artwave?
Say again, please.
Why'd you call it Artwave?
Artwave.
Artwave.
The name.
Why? Yeah, why? The reason dates back to our kind of initial days. That's a very good question. There were one kind of project coordinator, grant writer in the university, saying we said that this is our artificial wave project, and he was like, "That's too long name in this application field." And then one morning he said that I filed the application and it's Artwave. And then we were like, what? And then kind of it kind of developed so that we looked into Artwave. That's very common globally. So if we add surf, that's unique. And that's the story in a nutshell, Artwave. And yeah, maybe it's a bit artistic. Yeah. If no, yeah, there.
Any safety concerns?
Safety concerns. Yeah, good, very good. That is actually the first questions when we are presenting our technology. What if you get in there? What happens? But that never happens. When you, well, of course, naturally you can't dive there. That's forbidden. But when you surf, you are there on top of the back end wing, and this moves 2.5-3 meters per second forward. When you start falling here, and the wings are here when you have fallen to the water. If you go underwater, the wings are even further away. And at first we did kind of the mistake that once someone falls, we immediately stopped the system, and we were like, what happened? And kind of after a couple of pull-ins, the surfer said that don't stop it. We hit the wings if you stop it. Just continue. But even if the surfer is here, and every session we have, there is someone eager to continue till the end of the life, and goes on, and we stop the system here, and the wings go on the surface slowly, and even there is no safety concern, that there is always someone who kind of sits on the wings when the system is stopped. And basically our safety concern is about swimming skills, and people are prepared to do surfing, since what we have seen this summer is that someone who has been doing like office work for 25 years comes there and saying, I surfed when I was young and I want to paddle out, and we are like, okay, yes, go there and try it. And then the kind of the memory of that is there, but the skill and physical condition is not there anymore, and that is our safety concern.
Atso, have you talked about that to any? Have you talked about that to any official authority, or in Germany we have the TÜV or something?
Yeah, not in Finland, since they don't have any kind of understanding of surfing. They don't know anything about it. But what we have, the regulation in Finland is such that we are responsible for the safety of all the users as we are providing the service, and that is a risk to us. And we have to have a safety document where we have listed all the possible risks and our pre-planned operation if something happens. And that is kind of the what the authorities can come in and they can kind of have the inspection, and they want to see the document. And that is what is expected.
Yourself, the document.
Yeah, we write it ourselves.
Lucky you.
Yeah, they just want to know that we handle the thing. And if they have the inspection, we need to be prepared to explain them that we handle these things this way. And if something happens and we go to court, we are the ones responsible for it. And that is kind of the pressure. We are responsible and we feel it. Yeah.
What's the best case scenario? So do you need like a cooperation with the university to get like a scale model like run with the university for a river solution? Like get an association of a river surf club that gets you involved with the feasibility study and start from there?
Yeah, a good question. No, basically not. We can do it directly. We have all the expertise. But the local cooperation is really essential. So the kind of the local community and the commitment to do it is something that is needed. So we can provide the technical support and expertise, and even the delivery of all the components that can be done by the maritime industry network in Finland. But then, how it's done locally? What are the local politicians? What is the permitting process, feasibility study, and all that is something that needs to be done locally with local people. And our role is clearly to support that. And there, I think cooperation with the city and with the university and the surfing community could be fruitful.
Is there at the moment any project on the horizon where you can realize the proof of concept?
Yeah, several discussions, but as we have been discussing here even today and yesterday, it takes 10 years. So it's a slow game.
You said that on the bottom of the lake, you had no movement on the surface.
Yeah. So if you have, if the depth is 2 meters, you need to have rocks on the bottom of the lake, since the current is quite strong. It's around the wings. But if you have here 3 to 4 meters, it's just sand or even mud. So there are no visible movement here. But here, when we pull it there, we have the kind of stronger currents.
When I imagine the wing in the river, you think after the wave, the river bottom would be washed out, or would be?
Yeah, here, here, it needs to be studied, but the expectation is that the currents here go like this way here, so there will be some stress on the bottom of the river, behind the wave. Yeah.
Thank you.
Yeah, there even two.
And what about the maintenance of the system?
Yeah, maintenance of the system. You need to look after it and take it out of the water. Let's say once in the if we get the specification correct, that is quite kind of durable assembly. For instance, for our system, we know certain parts are wearing out. The wire rope system wears out, but the wings themselves, that's pretty stable. So maybe once in a season is a good idea. If you want to be really kind of on the safe side, it is really easy to get them out for the night, for instance, if you do a proprietary solution.
Thank you.
Just out of interest. So if I would say I want to buy your thing, so what would be kind of the price tag?
It depends, but if you do the wings to the river, that is kind of pretty straightforward. So the price is lower than having the engine there. And what we are talking about is clearly less than $1 million, maybe even close to 100,000 if you have the really simple wings there. And but need to consider also the project. So the feasibility study and the computation and all that, that is worth investing in. But that is, again, we are talking about maybe tens of thousands of euros maximum.
So the hardware would be around $1 million for the link.
Say again, please.
The hardware alone would be around $1 million for the link.
Yeah, I can't kind of get.
Just the hardware.
Yeah, the hardware. Yeah, and the kind of if you have the then if you increase the budget, you can start getting like more advanced materials. But if you consider the software and getting like the trimming optimized, then if you increase the budget, then you get like the kind of top-notch instrument there. But that's but that's making it the simplest possible budget model. That's the starting point.
Also, just like way of interest, if you could choose or design your surrounding for your prototype, and let's say you're aiming for a river, so I assume it's so just the optimal situation. If you could name this a river with the bridge pillar, there's a certain depth of, I don't know, and a flow ratio of 8-10 cubic meters. Can you point this out? What would be your optimal surroundings for a river?
The optimal surroundings in the river is that you have actually a quite small passage, so it's quite narrow, and then you have some drop there so that you can increase the flow speed, and then you have the attachment point like the bridge pillar. That would be optimal. And
so rather a narrow river, not a wide river bed.
Yeah. Narrow and shallow is that's good.
One more question about the river solution, Atso. What about the wings? There's a lot of debris in the water, like sometimes even trees are coming down the river. How sturdy are the wings?
Very good. That is when you have kind of what we have. This is something you need to model. But if you have kind of the flow is there and you have enough water, and the trees are flowing on kind of on the surface, they go quite smoothly over it. But if it's heavier stuff submerged a bit and they hit the wings, that's a more kind of challenging situation. But what we have learned so far is that if you have flow here, it usually gets kind of seldom anything hits the wings. So kind of I don't know the term, but you know when even when you have a tanker and someone wants to hit the side of the tanker, it's just not possible because you can't kind of penetrate the flow. If someone knows the term for the phenomenon, that's why I think the floating garbage just goes on the surface and kind of through the wings, and there is no harm done.
The water turbulence keeps the debris away.
Yeah, maybe that is. But if you have like ropes or nets or something like that, that's more challenging. Coming downstream. Yeah.